All right, welcome back. We're going to continue talking about action potentials. And a lot of people find this to be challenging, but I want to encourage you to spend the time with it because you're going to see this again when we talk about action potentials in neurons, as well as later on action potentials in cardiac muscle. So it's worth the effort because it's going to come up a bunch of times. So this is a graph of the action potential. Um, And one thing I like to point out here is for a skeletal muscle cell, the resting membrane potential is about negative 90 millivolts. So that means while the muscle is at rest before it's been stimulated, you have a situation like this one where the inside of the cell is sitting at about negative 90 millivolts, has a high concentration of potassium, and the outside of the cell is relatively positive, has a high concentration of sodium and calcium. So if you can make the muscle cell reach this threshold, which is negative 65, and that's just another typical value for skeletal muscle cells, you're going to trigger this all or none signal, the action potential. Now, what causes you to reach the threshold is if you have a big enough end plate potential. And the way you get a big end plate potential is by releasing a lot of acetylcholine onto the motor end plate so that sufficient sodium will enter to begin to open the voltage gated sodium channels. So what threshold is and why you get this big signal if you reach that value is it is the number at which the voltage gated sodium channels in the sarcolemma begin to open. And that positive change from the opening of your voltage-gated sodium channels is called depolarization. And that's occurring because you have a whole bunch of sodium entering into the cell all down the sarcolemma from the opening of these voltage-gated sodium channels. At the same time, that positive change in voltage that you got at threshold has also triggered the opening of your voltage-gated potassium channels, but they are slow to open and slow to close. So by the time all of this stuff has happened with your sodium channels, your potassium channels are just starting to open. And as your potassium channels open, potassium is going to leave your cell. You have positive charge leaving the cell. That's going to make your cell more negative. But also, your potassium channels are slow to open, but they're also slow to close. So for a minute here, you have this hyperpolarization where your membrane potential actually dips below your negative membrane potential very briefly. Note, as I put down here, that the end result of this activity, which is the release of calcium onto your myofilaments, you don't see that the effect of those calcium ions because it does not involve a large change in voltage. Also, you don't see any effect of the release of calcium, or the entry of calcium rather, into your synaptic knob because we are measuring here from the muscle. And also, it's not a large change in voltage. So let me try to explain that better. What was a terrible picture? This is supposed to be my synaptic knob, and here my muscle fiber. And so all of this stuff that we're talking about now, we're measuring with an electrode, either surface electrode or by penetrating with an electrode in the muscle itself. We're not measuring here in the neuron. So we're just looking at changes that are occurring in the sarcolemma of the muscle fiber. Okay, so what is happening in the sarcolemma of the muscle fiber? Well, I'm going to try to walk through it with this little diagram, and I hope that this will help. The first thing is that you have a nerve signal traveling down the axon. This is causing a bunch of positive charges to enter as sodium enters here. This triggers the opening of your voltage-gated sodium channels in the synaptic knob. As a result of that, I hope I just said voltage-gated calcium channels. anyway, this is triggering the opening of your voltage-gated calcium channels. As a result of that, calcium is going to enter into your synaptic knob. That calcium is going to bind to your vesicles, and it's going to trigger the fusion of those vesicles with the synaptic knob membrane, which releases acetylcholine into that synaptic cleft. That acetylcholine will then diffuse across that synaptic cleft, where it will then bind to acetylcholine receptors. In this case, these acetylcholine receptors have been bound, and so the big result of this is that sodium is going to enter through that motor end plate. Potassium also leaves, but like I've said a number of times, the important thing here is that sodium enters. This causes an end plate potential. Your muscle cell is becoming slightly more positive. Remember that at rest, this muscle is sitting here at negative 90 millivolts. So we are trying to get to a threshold value of negative 65. Although it's a negative value, it's more positive than where the cell normally sits. So if you release enough acetylcholine and you have the entry of enough sodium, which is going to occur when your cell potential reaches negative 65, that's going to trigger the opening of these voltage-gated sodium channels all down the sarcolemma. If you trigger those voltage-gated channels to open, they're going to open in sequence down the sarcolemma and T-tubule, and we call that all or none signal the action potential. Once it's triggered, is going to go all the way. So let's say that we have enough sodium entering our motor end plate to cause this to become positive. That's going to trigger these guys to open, your voltage-gated sodium channels to open. Sodium is going to then enter down in sequence through these channels that become open sequentially. And remember, these other channels here that I didn't label, your voltage-gated potassium channels, they have also been triggered to open at this point, but they are slow. It's sort of like those handicap doors. You push a button, and then like 4 or 5 seconds later, they start to open, whereas the sodium channels open right away. Okay, so this positive change in voltage is traveling down here, down my T-tubule, and that's causing this area around my terminal cisterna to also become more positive. So that change in positive voltage is going to open up my voltage-gated calcium channels on the terminal cisterna. So the terminal cisterna is then going to release calcium into my cell, and ultimately it is calcium binding to troponin that triggers your muscle contraction. All right, so those are the events in a nutshell. Let me show you one more time on this graph and ask you some questions here. All right, this value here, negative 90. What is this value? This is the resting membrane potential. That's where the muscle cell will sit normally when it is not being stimulated. How did we get here? Mostly because of the sodium-potassium pump. Okay, negative 65. What is this value, and how do you get it? Well, this value is the threshold. And why does it exist? It's because when you reach this number, negative 65 millivolts, which is a positive change, you start to open enough action potentials to, you start to open enough voltage-gated sodium channels to trigger an action potential. Okay, so here you see this little hump in my graph. What is this thing called? It's a change in voltage that doesn't travel down the sarcolemma, and so this is called an end plate potential, because it's a potential or voltage change that happens at the end plate, nowhere else. And what's happening to create this is that to create this upward deflection in the graph is that sodium is entering through our acetylcholine receptors. All right, so what's happening here? I have got enough EPPs. They're either strong enough or I had enough of them in a row that has triggered the opening of my voltage-gated sodium channels, and this is called depolarization. And so what channel is open here? This is a voltage-gated sodium channel. A bunch of voltage-gated sodium channels that are open. And what ion is moving? Well, it's voltage-gated sodium, so only sodium can enter that channel. And sodium is going into the cell. All right, and like I said in the previous graph, once you have triggered the opening of your sodium channels, you also trigger the opening of your voltage-gated potassium channels, but there's a bit of delay. So this downward part of the graph is called repolarization. And what channel has opened here? Well, as I just said, here you have opening of your voltage-gated potassium channels that were triggered to open at the same time as your voltage-gated sodium channels, but they are just slow to open. So what ion is moving? Well, the only ion that can move through a potassium channel is potassium. So potassium is moving, and it's going to leave your cell. All right, and then you can see down here, I dipped down lower than my resting membrane potential. And so what is this called? It's hyperpolarization. And why is this happening? It's because your voltage-gated potassium channels are slow both to open, and for this negative, extra negative area, it's important that they're slow to close, so they remain open a little bit longer than they need to restore your cell to your resting membrane potential. So for a moment it goes below -90, and that means that to trigger another action potential during this phase, you would need an even stronger stimulus. Okay. I hope that makes sense. One thing you can kind of think about to simplify this graph too, if the graph is positive, that means always it's because of sodium going into your cell. Where the graph is moving negative when it's going down, that's always because potassium is going out of the cell. There are a few different reasons why those things might be happening, but hopefully that will help you to think about this. All right. I'll talk about some Botox. Botox is a toxin that prevents the release of acetylcholine from your synaptic knobs. If you never release acetylcholine, then your muscle cell will never be stimulated to contract. And so that causes paralysis. Most of the time you get that from ingesting a toxin released by bacteria from canned foods, but then other people inject it willingly into their face to relax those muscles with the goal of making their wrinkles disappear. When it comes to muscle fibers in humans, there's a couple of different types, and the main kind of difference between them is between slow twitch type 1 and fast twitch type 2. These muscle fiber ratios do have a effect on your genetic ability to perform certain tasks, and like I said, it is controlled partially genetically, and as a result of your muscle fiber ratios, some people are better at producing force, so they'll be better suited to, let's say, sports like Olympic weightlifting or sprinting, for example, whereas others are better at sustaining effort, so they may be better at a sport like a marathon or a triathlon. And generally speaking, for the normal individual, like you or I, the difference between all of us is mostly down to training, just how much effort we put into physical training. But at the top levels, like in the Olympics, you have a much larger effect of your muscle ratio types. And you see this, very clearly in certain individuals, like this dude here on the left has a lot of fast twitch muscles. The fastest sprinters in the world have a lot of fast twitch type 2 muscles, which, as I'll show you in a second, also would look white. And, you see that difference between white meat and dark meat and a chicken, that you buy at the store, for example. But anyway, this dude on the left has a lot of fast twitch muscles, type 2, and this dude on the right has a lot of slow twitch or type 1 red muscle fibers. And you see a lot of, there's a stereotypical difference between people that are involved in power generation sports and people that are involved in endurance sports. And the reason that one of the reasons anyways that these muscles are so different is that, thought I had a better picture. Well, this is okay. In your fast twitch fibers, you have a whole bunch of muscle fibers and nothing else. So you've packed in the muscle fibers as tightly as you can. That's to the exclusion, for example, of blood vessels. And so these muscles are able to produce a lot of force, and they can do it quickly, but they also tire quickly because they don't have blood vessels to support aerobic cell respiration. Dark meat, on the other hand, it appears dark and more red because it has more vasculature, more blood vessels going through it. And because it has those blood vessels going through it, it is more able to perform aerobic cellular respiration, which more efficiently provides energy, so they can perform that whatever action they're doing, for a long period of time. And different muscles in your body are more likely to be fast or slow twitch. For example, your postural muscles are going to be more slow twitch because they're acting all the time, although they may not be exerting a whole lot of power or force at any one time. And nobody is all, slow twitch, and nobody's all fast twitch, and we all have different ratios of these muscles. But like I said at the beginning, if you have more slow twitch muscles, you're going to be better suited to sports like long distance running. The more fast twitch or the more packed your muscle is with muscle fibers versus blood vessels, the better you'll be at power generation sports like sprinting. And then, of course, some sports also select for having a blended ratio. You need to be good at both power and endurance. I think the last thing we'll talk about is muscle tension. You can see here they're measuring the tension or the force produced by this muscle. And they're providing first a electrical stimulation to the muscle, which is going to trigger an action potential in the muscle. And you can do this to a living subject. You even sell these things probably on Amazon, where you put these little electrodes on your back and deliver a small current into your muscles, and it makes you twitch. That's triggering the action potential of your muscles. Anyway, you can see that between the electrical stimulus and the period of contraction of the muscle, there is a delay. And that action potential that we looked at happens with the speed of electricity, so it's very fast. But the cross-bridge cycling takes some time, so there's going to be a delay between the electrical events of your muscle's action potential and then the actual mechanical events of that muscle contraction. Anyway, the only reason I'm showing you this is because this is a way you can measure the force generated in a muscle contraction, and then you can use that to investigate various things like how do you control the amount of force that your muscles are putting out. And one of the main things you can do is vary the number of motor units that you are using. So if you increase the number of motor units, you're going to increase the force. Excuse me. And at some point you reach the maximal force of a muscle, the maximum number of motor units that can be recruited by a muscle. If you have a few number of motor units that are getting activated, you're going to activate less force because that means less muscle filaments are contracting at any one time. You'll increase a force by increasing the number of motor units that you're activating. Some sports, like particularly Olympic weightlifting, but any sport which requires power generation, one of the things you learn, even if you're not conscious of doing it, is to recruit as many motor units as fast as you can. And that's particularly true in Olympic weightlifting, where the first, half a second or less of the motion is what determines the success of everything else. So they have to shoot the weight up off of the ground as hard as they can, as fast as they can, and that depends on recruiting a lot of motor units. So just to put this in an example, this is showing you in a bicep. If you had a light load, maybe you would only recruit motor unit 1, which is these, red ones. And if you had a heavy load, you might recruit all 3 motor units. And that's just going to cause a greater number of contractile elements to slide past each other, resulting in a greater force. Just a couple of terms here. An isometric contraction is when you contract your muscles but don't actually move them. So for example, let me push this table here. This table is against the wall. So I'm making a lot of muscle tension, but I'm not actually moving anywhere. That's isometric. And the isotonic contraction is when you contract your muscle and also change the angle of your bones. So in a concentric muscle contraction, you shorten the muscle, and in general you shorten the angle between your bones. And an eccentric contraction, the muscle lengthens. And to give you another example, concentric. Yeah, let me start like this. That's a great picture. There's a dude doing a pull-up. As he's pulling up, his muscle is getting shorter, and this is concentric. But as he's letting himself down, as long as he's not just flopping down completely, you come out of a pull-up slowly with your muscles still contracted. This would be an eccentric muscle contraction. And it looks like, and I guess it's sort of important for exercise science as well, it looks like that most of the time muscle soreness is caused by eccentric contraction rather than concentric contraction. And you may have noticed, for example, when you're riding a bike, I have no idea how to draw a bike. Anyway, when you're riding a bike, basically you're only making concentric contractions because you're just pushing the pedals down, unless you have those fancy clip-in things and you can pull them up as well. But anyway, most of the time you're pushing the pedals. You never have your muscle lengthening under tension. And so bicycling is can be an exercise that you can do without really experiencing soreness other than in your butt from the seat. And speaking of exercise, it's good for, of course, a number of reasons. You can increase the number of mitochondria. That's going to allow you to better produce energy. Hypertrophy is the increase in the size of the skeletal muscle, which results from more mitochondria, more glycogen, and more myofibrils, but it doesn't really result from more muscle cells. So the muscle cells get bigger, but you are not generally getting more muscle cells when you work out. Atrophy is the opposite. When you're sedentary, you'll experience a decrease in muscle fiber size, loss of mitochondria, lower glycogen reserves, etc. So, like I said, hyperplasia, which would be an increase in the number of muscle cells, is not thought to occur normally with exercise, although maybe you can get there with some human growth hormone or something like that. People try, but I don't know if they are successful or not. Anyway, that's it for Chapter 10. I'll see you guys next time.